this video, we're going to analyze a truss using the method of sections. The given truss and loading is basically we are looking to find the forces in members CD, CJ, and KJ. So this is the more appropriate method. Recall that the method of joints would be appropriate if we needed to find the forces in all the members composing this truss. Let's first come up with an approach. So first thing we want to do, since in order to cut through members KJ, CJ, and CD, and if we don't find any of the reactions, we would end up with more unknowns than we have equations of equilibrium. So the first thing is, using global equilibrium, we would find the reactions at either support A or G. In this case, we're going to select support A. The next thing is we'll cut through, after we cut through the members CD, CJ, and KJ, we'll isolate the left-hand section and draw a free body diagram. Once we have that free body diagram, we can then apply equilibrium to find the forces in those three members. So let us first find the reactions at A. So we have A, Y, and AX. We also have G, Y for that roller. So I'm only needing the reactions at A, so I'm going to go ahead and apply equilibrium. Sum of the forces along the X equals 0. Notice we don't have any other forces acting on the X except AX. So that's equal to 0. And then from the moments at point G, we'll be able to get the reaction at A. So we have a positive moment 6 times 2 meters, 6 kilonewtons times 2 meters. Positive moment 8 times 4. And then 8 times 5. And then we also have 10 times 4. And finally, the 12 times AY is a negative moment. And so from this, we're going to get an AY equal to 10.33 kilonewtons. So now that we have the reactions at A, we can go ahead and isolate the left portion or the left section of this, where we have reaction at A of 10.33 kilonewtons. And so now that we have cut through these members, we can draw the internal forces. This is force CD. This is force CJ. And finally, this is force KJ. This is essentially a rigid body, free body diagram. So we have three equations of equilibrium available. And in this case, I'm going to use the moments about point C and moments about point J, as well as the forces along the Y. So let us go ahead and apply moments about point C. And the reason for that is because we want to get that force KJ. So force KJ produces a negative moment of KJ times 3 meters. And then notice force, the 5 kilonewton applied force does not produce a moment because it passes through point C. The 4 kilonewton force, however, produces a positive moment of 4 times 2. And then the reaction at A produces a negative moment of 10.33 kilonewtons times 4 meters, from which we get the force KJ equal to negative 11.1 kilonewtons or 11.1 kilonewtons in compression, which will indicate with a C in parentheses. Now we sum moments about point J, which is not on our free body diagram, but it's up here. And it's 2 meters from point C. So first thing is find the moment of force CD, and that's going to be a positive moment of FCD times 3. Then the force, the 5 kilonewton force, notice that produced a positive moment, 5 times 2. The 4 kilonewton force produces a moment of 4 times 4. And finally, the reaction at A produces a negative moment of 10.33 times 6. Set that equal to 0. So from that, we get FCD equal to 12 kilonewtons in tension. And we'll indicate that with a T. So the last thing we want to do is sum forces along the Y. And that will be to get the force CJ. The angle that this force makes is going to be a 2, 3 square root of 13 angle. So our component of CJ along the Y is going to be equal to positive 3 over the square root of 13 times FCJ. And the other forces in the vertical direction are the negative 5 kilonewton, the negative 4 kilonewton, and the positive reaction at A, 10.33 kilonewtons. And this is equal to 0. From that, we get that the force CJ is equal to negative 1.60 kilonewtons or 1.60 kilonewtons in compression. I hope that this was useful, and see you next time.